Okay. So, my dear students and my dear faculty and my dear colleagues, so on behalf of the Guru Nanak Institute of Technology and the Institutions Innovations Council, (IPANO), so I would like to invite today's guest for delivering the lecture on the mechanics of solids. So, the invitee is Dr. S. Salman Raju, Associate Professor, Department of Mechanical Engineering, CBIT. So I thank you, sir, for accepting our invitation. I
Thank
welcome you to deliver a wonderful lecture and expert lecture on the mechanics of solids. So it is an honor and it is fortunate to have such a great person. You have the very good research exposure and you have contributed a lot of research in the various activities. You have the IIT background. So I welcome you all to deliver a wonderful lecture, valuable lecture to our budding engineers, our second year students. Thank you, sir. And now I will hand over the session to you. Thank you, sir.
thank you, sir, and thank you so much for the kind words. And at the outset, I would like to really extend my greetings to the head of the department, Vijay Kumar sir, and Srihari sir and Raghu sir for having coordinated this event. And thank you so much for having me here. And very good morning, dear wonderful students of second year. I came to know that you are in the second year. So I would like to share some of my thoughts with regard to the mechanics of solids and some insights into that. And more than my own presentation, I do wish all my great students anything that comes to your mind and where you want to really debate with me, anything that comes to your mind, you try to share and I will try to answer you to the extent possible. So let this I wish this session to be more interactive because already the semester is ended for you. Any doubts or something related to mechanics of solids, you can share with me. And myself, because I have done MTech in solid mechanics and design from IIT Kanpur, I definitely hope I can answer your queries to a great extent. So having said that, now let me start sharing my presentation. Yeah, Raghu sir, can you give me permission to share?
Yes, yes, yeah, yes, sir. Yes, sir. You can, yes, sir. Now you can share it.
No, sir. Raghu sir is still sharing. Is presenting. Once he closes, I think I can get into it.
Yeah, yeah. Yes, sir.
Yeah. Thank you. Sir, is my PPT visible to you all, sir?
Yes, sir. Yes, sir.
Thank you so much, sir. Thank you. So yeah, dear loving students, because as your HOD sir has rightly quoted, you are really the budding engineers and who have a great future. And tomorrow you are going to be in industry, especially in the manufacturing industry, and where lot many activities are involved. So with regard to that, we have a different specialization in mechanical engineering, and one such specialization is what we call it as a design engineering. So when it comes to the design engineering, the basic objectives for an engineer or a professional who is going to execute his duties in an industry is to design the components. And the components in the sense, variety of components we are going to use even in day-to-day life at our own houses. And I'm sitting on a chair and I'm sitting on the bench and I write with the pen and I do wear a shirt, and there are all the components we are going to use. And all these components need to be designed by a design engineer. So then comes a very big question. Why actually I need to design? And if not I design, what is the danger that I am going to face? So in this aspect, this design engineering has acquired a lot of importance, and therefore we need to really have a solid insights into this design phenomena to come up with the designs in the mechanical engineering field. So having said that, now I will take you first of all. See, for example, we see so many components and in and around us, automobiles and aerospace and the bench I am sitting and the chair I am sitting, all are the components. So which have been basically designed by the great engineers. So when it comes to the design engineering, the first and the foremost thing a design engineer need to keep in mind is the product I designed, is it fulfilling the function or not? So when it comes to the performing or meeting the needs of the customer, then comes a very big challenges for an engineer. So let us keep few of the simple aspects aside and let us focus only on the major aspect of the design engineering. So as a mechanical engineers, dear loving students, the component what I design, the component can be a gear, a belt drive, or the beam or the springs or the gears or the bearings or innumerous components we have, including the aerospace aeroplane bodies and the ship propellers and the ship bodies, and everything need to be designed. So once I design the basic aim or the target, what I keep in my mind is this component for a designed period of time, I don't want this component to fail. So the first and the foremost point for a design engineer is the component I design should not fail. So here I have shown a few of the what you can say these things so that we'll get some idea as to how the failure is going to be. See, this is one of the component that has failed in fatigue. Of course, fatigue is a big term. Down the line, you will understand. So this is what is the failure. And here, if you see, the gate tooth, okay, so once it is connected to some component, it has broken. And this is a railway wagon wheel. Imagine, see, this is how it is broken. And this is the very famous component which we all know, it is a bolt. So this bolt has broken at these positions, and this is one such component. Now tomorrow we all need to answer these questions and we need to give solutions to them, and we need to come up with designs that do not cause failure. So when it so the first statement you all should keep in mind is as a design engineer, I should see that the component will not fail. Very good. So well, we have said I don't want the component to fail because I want to arrest failure. Now comes the next question: what actually I mean by a failure? What do I mean by a failure? That is very, very, very important. And having said that, failure has got its own definitions. And with regard to the shirts, what we wear, we wear a shirt for a few days. After that, we try to throw it off. We know what is the failure with regard to the shirt. Once it gets faded, or once the collar gets torn off, or once the button starts moving off, or once a tear comes, we do regard that one to be a failure. But when it comes to the mechanical components, what do we mean by failure and how do we justify? So with regard to that point of view, dear friends, failure is basically associated to three components in mechanical engineering. So failure could be the first factor, could be because of the fracture. So this is fracture that may lead to the failure. And the second one is because of the yielding. Because of the yielding. So we can even think of the failure in terms of yielding. And the third failure, what we need to keep in mind is the stability failure. So these terms, though look very simple for us to listen to, lot much of engineering has to be understood in order to really understand what actually in by these failures. So failure of a mechanical component is attributed to any one of these three phenomena. So for example, if you see here, the bolt what we have seen, see, this has become into two pieces. So this has become into two pieces means here a clean fracture has happened, here the fracture has happened, here the fracture has happened and the fracture surface has come, here also the fracture has happened, here also the fracture has happened, and here also the fracture. So what is a fracture? So fracture itself is a very big term, but to make you people understand, fracture is nothing but creating two new surfaces. When a component breaks into two pieces, when any component, you can take a pen break into, or a paper tear into, a biscuit you break into. Once you break a biscuit into two pieces, you are going to generate new surfaces there. So fracture is associated with the breaking of a component into two or more pieces, wherein the two new surfaces are going to form. So accordingly, there is a very big study. In future, you will study the subjects such as fracture mechanics and the linear fracture mechanics and non-linear fracture mechanics, and it's altogether a very big science. So fracture is associated with the breaking of a component into two or three pieces. That is one. Secondly, now let us say yielding failure. Why we do call a yielding failure? Just a small example to only for my dear second year budding engineers to just give you a glimpse. Say for example, there is a roof in our houses. We have a roof and there is a fan rod. We know we all use fans at homes, and there our fan would be rotating. It has blades, so it would be rotating continuously whenever we put on the switch. Okay, people are here at this place and they would be sleeping comfortably, or they would be walking here, and they will get the air distributed here, so that because of evaporative cooling we feel cool. That is the working principle of the fan. So with regard to the design, and let us say this fan rod is made up of some material. This fan rod is made up of some material, and see, we do not use chalk piece material for making the fan rod, and I do not use plastic for making the fan rod. So mostly we do use the mild steel. Why? Because as a design engineer, I know what are the properties of the mild steel, and I am sure this can only serve the purpose with regard to the fan rod. Okay, so over the period of time when the fan is rotating, it puts lot of axial weight as well as the rotational loads onto the fan rod. Let us say somebody used a material who is not an engineer, chosen some arbitrary material, and let us say after 3-4 years of rotation, let us say initially the fan location is here, and now let us say the fan, what you can say, this one I'll choose some different color just to make you people, yeah. So let us say this is the position when the fan is brand new and attached to the roof. Over the period of 10 years, let us say the fan rod length has increased and it has come to this position. It has come to this position. So this much of elongation has happened in the fan rod. So because of this elongation, though the fan is rotating here, according to us, it is a failure, because I didn't want the fan to rotate at this position, because I want the fan rod to be at some particular height. Because if the fan rod extends and comes down, people in the room cannot move their hands freely. When they move their hands, they know they get hurt by the fan. Okay, so here what is happening? Fan rod is not breaking. It did not get into two pieces, but it has elongated so much, and it is into a plastic elongation, and this elongation is permanent. It after, if I put off the fan also, it will not go back to its original position. So this is what we call it as a permanent deformation. So this permanent deformation comes in the component once a particular state of stress for a given material is crossed. Every material has a stress, and what we call it as a yield stress. You all know that yield stress, which you will get by drawing the stress versus strain curve. So once the applied stress exceeds the yield stress, the material gets into a permanent deformation or a plastic zone, which is irreversible. So this type of failure is called as the yielding failure. So pen kuda manam rastu unte, pen over the period of time you write, it may be initially straight, but over the period of time, because of the pressure we apply, the pen may become like this. And once it becomes like this, I cannot write it very comfortably. So this is what is yielding failure. Or even the benches you are sitting in the class, initially they are horizontal, or after 10 years, let us say the bench has become something like this. People cannot sit comfortable. So this failure is nothing but the yielding failure. Though these look very these things, but these are the research topics, and lot more content is there for you people to really get into them and take up further studies. And third failure is a stability failure. So in stability failure, what happens, especially this is with regard to the columns. You might have studied columns. In columns, it is instability. Stability is the criteria. And this stability, when it loses for a component, we don't know whether it can be get into a fracture or it can get into a permanent deformation. Okay, so these are the three modes of failure a mechanical component is going to face. Now comes the question, okay, I have these things, then how I should take care of these things so that the component tomorrow I design a gear, belt, or a bearing, or the shaft, or anything will not fail in any one of these three things. So in this aspect, there comes a wonderful thing. The one thing that leads to all these failures is a very, very wonderful term, what we call it as a stress. What we call it as a stress. So all these failure modes, that is either the fracture, yielding, and stability, they can be attributed to one powerful quantity in engineering, and that is what we call it as a stress. What we call it as a stress. Okay, so now with regard to this, I will try to throw some light on the stress, and because I'm exclusively asked to answer the principal stresses and theories of failure. So I want to take you all people in that direction. And at any point in time, dear loving students, if you have got anything to ask me, please unmute yourself and you can keep asking me. Right. So these three modes of failure are called, attributed to the stress. Now comes a question now. What is stress? For example, you take this component. Why this component only failed here? Why it did not fail here, why it did not fail here, and why it did not fail here, why only at this particular location it has failed. Here comes the very, very important observation made by our great scientists much before us, and what they have presented is whenever now come back here, yeah. So let me throw just some light on what you can call it as uh, stress. So any component I design or you design tomorrow, any aeroplane, ship, or any or household appliances, even the stove and the motorcycle and the shoes, watch, everything is meant to carry some load. So what is going to happen is it's very, very important for an engineer to understand what actually is happening at a point in a material, because this I want to quote, because I want to tell you people what is stress, and then I want you people to be connected to the failure, then come up with the principal stresses, then to the theories of failure. So that is how let us move step by step. So now let me say, for example, you have taken some material. This can be a random material, any material it can be. So any material means you have variety of materials. Plastic is a material, chalk piece is a material, wood is a material, iron is a material, aluminum is a material. So variety of materials we have. So once you have a material and take some volume, I made a component of mobile or the bench or the chair, where we are going to apply the loads. Any component, if you observe, mostly we do apply the loads only on the surface of that particular component. So this particular body, what I have chosen, it has got the surface, and any loads we apply, they do act only on the surface. They do act only on the surface. So upon the surface, I may apply the point loads, and sometimes I may apply the distributed loads, and sometimes I may apply varying loads, or like this I can apply variety of loads onto the surface. Very good, very well said. We have applied the loads. Okay, what next? See, the target is whatever the loads I am applying, I want this particular body or the material to resist it. If it doesn't resist, then it is going to just move as a rigid body or something. It may flow very freely like a perfect plastic material, and which is not going to hamper the very purpose for which we have designed. So whenever we apply the loads, very important point, my dear friends, this particular material or the component has got infinite number of points. See, this is the great truth you all should understand, though at your level seems to be a bit easy, but you need to understand. So every component or the material volume has got infinite number of particles. So what is going to happen whenever I apply the loads onto the surface of a particular body? These loads are going to be transmitted to each and every point in the component. So that means each and every point in the component is going to contribute to the load carrying capacity. And here, we as an engineers, we make so many assumptions, because if the effect has to be transmitted to each and every part in the material, the underlying assumption is there should not be any gaps in the material, and the material should be a continuous material. So mostly whatever you study in mechanics of materials or design of machine elements or everywhere, we make one big assumption that the material or whatever we are assuming, we assume it to be a continuous material, a continuum. There is a very, very powerful word we use in mechanics of solids, continuum. Continuum means all particles are intact and there is no gap between the particles and there are no voids. Okay, having said that, once I apply the load, each and every particle will try to contribute its best to carrying the load. Then we know we all have defined the stress. So in that aspect, people started defining the stress. When I apply the load, member will try to resist. So this resistive force offered by the material per unit cross-sectional area is what we call it as a stress. Okay, the resistive force offered by the material per unit cross-sectional area is what we call it as a stress. And now comes another doubt might have come to you. What is this area you're talking? So when I talk of an area, then definitely we should choose some area in the material to define the stress. So with regard to that, what I do, this lump sum material, now let us say I have cut it. I have cut it somewhere else. By taking some plane, I have cut it like this. Imagine we have cut it. So after cutting, it is going to look like this. This is a cutted surface. Okay. This is a section surface. On this section surface, let us say it's a parallel surface. Now I want to go to only one point, dear friends. Only one point I have chosen. This point is point Q. I went to only one point in the material. Having gone to one point in the material, now what I do, what is happening at this particular point, how much stress is coming at that particular point is the ultimate goal, which every design engineer is worried about with regard to ANSYS packages or fluid packages or any mechanics. Basically begins with this. So we need to go to this particular point, and because point is dimensionless and there cannot be any area for a point. So what people started doing, surrounding this point, people started taking an infinitesimally small area. Surrounding this point, I am going to take an infinitesimally small area, which I do denote it as delta A. So delta A is a very, very small area I have taken. So having taken this delta A, delta A is a plane, and this plane, upon this plane, there can act only two stresses. One stress can be perpendicular to the plane. Another stress can be parallel to the plane. Stress can be perpendicular to the plane, parallel to the plane. So perpendicular to this particular white collar area, let us say the force acting normal to that is, let us call it as a delta Fx. And another force which will act parallel to the plane, let us do name it as delta Vx, because capital V generally we use for shear forces. So therefore it is delta Vx parallel to the surface, and normal to the surface is delta Fx. Very good. So now over this small infinitesimal area, I know what is the force acting perpendicular to that, and I know what is the force acting parallel to the plane. So having known them, people have defined the stress as it is the resistive force offered by the material per unit cross-sectional area. Unit cross-sectional area. Now, having said that, now look into this third figure. This is the fundamental. So if you understand these fundamentals, I am very sure remaining big problems, they are very, very simple. Anybody can solve. Okay. Yeah. So now let us come back to this Q, dear friends, and this white area is the area what I have taken, and over that small infinitesimal area, let us say delta Fx is the load acting, and this parallel shear force, see, parallel to this one, I have infinite directions, but normal to surface only one direction I have, because for a given plane normal is fixed, but within the plane I can have infinite directions. So therefore, in order to get rid of this, what people thought of is they try to split this in-plane shear force into two components. So based upon this is the x-axis if I take, dear friends, and this is y-axis. So this delta Vx, we do split into two components. One is delta Vxy acting along y-axis, and delta Vxz that is acting along z-axis. Why we are splitting? Because there are infinite directions for the shear force. In order to be concise and want to get unique solution, I need to definitely split into two directions. So finally, by now you all great people should have understood, at a given point and at a given plane, at a given point, at a given point on a given plane, there are going to be three force components. One is along x delta fx, one is along y delta vxy, one is along z delta x delta vxz. Now I know the forces. I know the area of this small infinitesimal portion what I have taken. I do call it as delta A. So by definition, all people know that stress is defined as stress along x. Normal stress, we do denote it with sigma. So normal stress along x is equal to limit delta A tends to 0. Very important, this term. Limit delta A tends to 0. So when delta A tends to 0, that means area is getting converged to a point. So delta A tends to 0. Delta Fx is the force acting along x divided by delta A will give us the normal stress acting along x direction. That is done. And what about the two other components? Those two are the shear, because in plane loads we call as the shear loads, and the corresponding stresses as the shear stresses. So tau xy, shear stresses, generally in any book they do denote it with tau. So tau xy means, dear great people, we need to pay attention to the subscripts here. We have two subscripts, one is y and one is x. So this y indicates the direction of the stress, very important. Second subscript index the direction of the stress, and the first index indicates the normal to the plane. So tau xy means it is the shear stress acting in the y direction on a plane whose outward normal is in the x direction. So if you read a very good foreign author books, they people are very specific about the notation. But at your level, at second year, third year, without them also, without knowing what they are also, we can solve so many problems and we can keep getting very good marks, and that runs the life for us, and it's no issue for us. So having said this, then delta equal to 0, the shear load acting along that axis divided by area. So like this, we can define the third shear stress, tau xz. It is in the z direction on x plane. So conclusively, dear all students, by now, having understood the different types of failures, three modes of failures, I told you failures are related to the stress, and at a point, the stress on a plane only, can be denoted by three stress components. So these are the three stress components. One plane at any point in a material can possess. These are the three components of stress any point in a material can possess. So plane is going to be specified by three stress components. One is normal stress and two shear stresses. Okay, now having said this, dear friends, and if I take a point in a material, for example, this is the material I have drawn, and if I go to one point in the material, you all know that how many planes we can draw passing through this particular point? Very obvious answer. You all will answer me. Passing through this particular point, I can pass infinite number of planes. Infinite. So I have infinite planes at a point, and each plane has got three components of stresses. So imagine the number of stress components I need to understand at a point in a material. Okay, it is anyway infinity, and 3 times infinity, again it is going to become infinity. So infinity is undefined, and solving that infinity lifespan is not sufficient, so there is absolutely no solution to that. Here actually what happened, the great people have come to our rescue. వాళ్ళు ఏమంటున్నారు అని అంటే, if we take any material, dear friends, and go to one point in a material and surround at this particular point, there is no need for you to know the stress components on these infinite planes, but it is only sufficient if you know the stress components acting on only three mutually perpendicular planes. అంటే ఈ పాయింట్ దగ్గర ఇన్ఫైనైట్ ఇన్ఫర్మేషన్ నాకు అవసరం లేదు, కానీ నాకు ఓన్లీ I need information about only three planes which are mutually perpendicular to each other. So at this particular point, I need to draw three orthogonal planes. And this investigation is brought in by Cauchy, a great gentleman who has done a lot of research work with regard to continuum mechanics, and he has come up with so many equations which we use when we really deal with the continuum mechanics. So through Cauchy, because he said that no need to worry about infinite planes, but worry about only three mutually perpendicular planes. In that aspect, there has come a great innovation, what we call it as a stress element. People have evolved with a concept called stress element. So what is a stress element at a point? At a point in a material, stress element is nothing but an infinitesimal cube. At a point, we all can draw the cube. It is an infinitesimal small cube. Infinitesimal means everything tends to 0. So in this cube, you know that obviously it is defined by 6 planes, but 3 of the planes are, this is 1, let us say this is 2, and this is 3, dear friends, and these 3 planes are orthogonal to each other. So if I want to know what is the state of stress at a point, I need to worry only about these 3 mutually perpendicular planes. And as we have seen just before, each plane is specified by 3 stress components. So 3 plus 3 plus 3. So finally, before moving forward, state of stress at a point is defined by 9 stress components. Very, very important conclusion. State of stress at a point is given by 9 stress components. But if I write them, you all can understand. Anyway, they are shown here. One is, let us say, normal stress along x, sigma x. Normal stress along y, sigma y. Normal stress along z axis, that is sigma z. So 3 normal stresses and 6 shear stresses, because each plane we have seen just before, each plane is characterized by 2 shear components. So this is the x phase, that means whose normal is in the x direction. It is going to have 2 shear components. One is tau xy and tau xz. See the direction of arrows also. Very, very important. Similarly, on the y phase, I have tau yz and tau yx. And on the z axis, I have tau zy and tau zx. I told you what do we mean by these subscripts. Very, very important. So now, out of these 9 components, it is again due to Cauchy and by using momentum equilibrium, because everything finally has to be in equilibrium. And out of all these 9 stress components, things have to be in equilibrium. So if you write that momentum equilibrium equation, because derivation takes a lot of time, I'm not getting into that. We can easily prove that out of these 6 shear components, only 3 shear components are independent, for the reason shear stresses are complementary in nature. This you can by heart, and that will run the life, because you are just the beginners and second year students. So you can remember that shear stresses at a point in a material are complementary in nature. So what does that mean? That means tau yx is equal to tau xy. So indices gets exchanged. So x place y takes and y place x takes. Then these two are going to be equal. That means if I go to 1 or 2 planes, if you take, dear friends, and if you apply shear stress here, one if you apply, by default another will come at free of cost. This is what is complementary. Complementary means without cost. Complementary books or complementary gift, something like this. So people have proved that there are theories that will tell us shear stresses are complementary in nature. So because of this one, out of these 6 shear components, only 3 shear components are independent. And finally, at a point in a material, The material can be homogeneous, non-homogeneous, and anisotropic or isotropic, monoclinic, orthotropic. Nothing to worry. But every point in a material can have 3 plus 3, that is a 6 independent stress components. Okay, though we have 9 components, because of complementary nature of shear stresses, we do have only 6 shear stress or 6 stress components at a point in the material. Very well said, dear friends. Having said that, now let us move and try to connect ourselves to the failure of the components. As I told you, failure can be realized in terms of fracture, in terms of yielding, and in terms of stability. So these 3 terms are connected to the stresses. Now comes. Yes. So in a 3-dimensional scenario, because we were discussing just before, X, Y, Z axis. Whenever you work in X, Y, Z axis, dear friends, you know very well, enough studies you have made, it is nothing but a 3-dimensional space. So in a 3-dimensional space, we have 6 stress components. Aute, working the problems in 3D is very laborious and very complex under few circumstances. అప్పుడు చాలా మంది ఏం చేసినారంటే, ఇన్స్టెడ్ ఆఫ్ వర్కింగ్ ఇన్ 3 dimensions, is there a way for me to reduce the problem from 3D to 2D? So enormous theories are there, enormous people have come up with their own proposals, and in this regard there are enough mechanisms for us wherein we can convert a 3D problem into a 2D problem. So when I come back to the 2D problem, one such powerful problem what we need to discuss is plane stress. So మీరు చేసే ప్రాబ్లమ్స్ వెదర్ ఇన్ ద ఫస్ట్ యూనిట్ కానీ, సెకండ్ యూనిట్ కానీ, థర్డ్ యూనిట్ కానీ, ఫోర్త్ యూనిట్ కానీ, మీరు చేసే అంతా కూడా దే ఆర్ ద ప్లేన్ స్ట్రెస్ ప్రాబ్లమ్స్. ఎందుకు ప్లేన్ స్ట్రెస్ అంటే, ఇన్ ఆల్ ద ప్లేన్ స్ట్రెస్ కేసెస్ వీ ఆల్వేస్ ట్రై టు నల్లిఫై ద స్ట్రెస్ యాక్టింగ్ ఇన్ ద థర్డ్ డైరెక్షన్. So all the stresses, if I assume in the third direction 0, that type of condition, what I do achieve, we do call it as a plane stress condition. Another powerful problem is there, plane strain. But mostly we do not discuss in second, third and fourth year subject, because plane stress is a bit easy when compared to the plane strain. So plane stress is one state of stress. And for example, shaft is there. You all have studied torsion. Say for example, torsion of a shaft. It's a shaft. You have subjected it to torsion, twisting movement. Then every point you take on the surface, upon the surface, you know, at this particular point, we are very sure only 2D stresses are going to act. The stress in the third direction, we can make it equal to 0, and therefore this problem can be modeled as a 2-dimensional problem. Even a cantilever beam 2D, and like this many problems what we study, we can study them in the 2-dimensional domain. So in plane stress condition, the thing is, dear friends, all the stress components in the third direction will go to 0. Sigma Z, tau Zx, tau Zy, these will go to 0. Okay, so this condition is called plane stress condition. So if I draw the plane stress condition, and if I draw the same infinitesimal cube, and if I make this stress component 0, I am left with only, because 3 have gone 0, I am left with only 3. What are they, dear friends? One is sigma x is left for me, and the sigma y, and the third component is tau xy. And see, these two magnitudes are always same because of complementary nature. And if it is towards right, then it should be opposite. If it is like this, then it should be like this. So complementary means that they should come towards each other, or they should move away from each other at a point in a material. So we are left with only 3 stress components. So generally, instead of drawing the cube, people try to show it as a plane, but it doesn't mean it's a plane. It is actually, it is having some Z direction that is perpendicular to the presentation what I am making. Okay, yeah, so beautiful. So finally, before I take you to the principal stresses, at this point in time I want to tell you, with regard to the plane stresses, at any point in the material I am going to have 3 stress components. One is sigma x, one is sigma y, dear friends, and the third one is one shear stress. So 2 normal stresses and 1 shear stress are only the components I am going to have with regard to the problems in plane stress. Okay, and all other components we do assume it equal to be 0. Yeah, now comes the very important discussion and important point. Here I want to tell you. For example, see this problem. It's a real-time problem where you have a pole, and the pole is fixed to the base with the help of the bolts and nut mechanism. You all know as dear mechanical students. And now let us say it is subjected to, this is x-axis, and this is y-axis, and this is z-axis. Just let us investigate what can happen to this problem. Along y-axis, there is acting a 17 kilonewtons of force in the negative y directions. And you know very well, when the load passes through the axis, we do call it as an axial load. And with regard to axial load, having made the Saint Venant's simplification, you know how to calculate the stress for the axial load. Directly is equal to P by A. Because exams are coming near, I hope you all have remembered. Stress is sigma is equal to P by A, and delta is equal to PL by AE. I hope you all have remembered by hearted these particular formulae. Delta is equal to this, and you can even calculate the strain, because stress by strain is equal to Young's modulus. Okay, so with regard to the axial load, these are all the things I can calculate. And apart from this axial load, this pole is even subjected to a twisting moment of 3.75 kilonewton meters. Apart from this, it is equally subjected to a pull, or the pulling force of 3.2 kilonewtons at this particular point in the z direction. See, now you are a design engineer, or tomorrow you are going to become a powerful design engineer. Then comes, my dear great people, can you suggest me what material should I use for this pole, and what should be the dimensions I should use? This is what is the design engineering is all about, which is very much connected to the mechanics of materials. So mechanics of materials is nothing but understanding how a particular material will behave when it is subjected to external loads. See, rubber ball, I can easily compress it, but I cannot compress a steel ball. So its response is different from the rubber. So this is how engineer is more worried about the deformation patterns in mechanics of materials. So now it's very, very tough for us to decide, because of all these loads, where actually it is going to break. Means, let us say this pole is breaking into two pieces. Then at which point, because this has got infinite number of points, dear friends. So at which point the initial crack may begin, a very big challenge. Out of infinite points, I need to choose one point where the probability of creating a crack is high. Okay. Secondly, if it is failing in yielding, let us say it is undergoing permanent deformation. So if it is undergoing permanent deformation, I should see at which point there is a more probability that this permanent deformation is going to come. Okay. And thirdly, if it is a very long column, and if you think it is getting into instability, then you should think of Euler's critical load or Rankine's critical load, which will make this one into unstable and the failure. Okay, so right, so it's a very, very complex problem, but as a beginners we can make an effort, because if I take one point here on the material, one point here, and if I model it as a 2D, at this particular point, dear friends, I can calculate the three stress components. One is sigma x, I can calculate one is sigma y, and I can calculate another stress, what we call it as tau xy, if I model it as a two-dimensional problem. And there is a mechanism to calculate these stresses. Sigma x, for example, this is sigma x. Okay, so the stress in the sigma x is going to come only because of what you can call the compressive load, what I have applied here. This will produce a stress. This will produce a stress in the y direction. And this 3.2 kilonewtons, మనకు అందరికి తెలిసిపోవాలా 3.2 kilonewtons ఏం చేస్తుంది? It is trying to bend the structure. So we need to model it as a bending problem, and from bending equation we should able to calculate what is the corresponding stress. And this is a twisting moment or the torsion from T by J is equal to tau by R, that is equal to G theta by L. We can calculate what is the shear stress that is going to come. So finally, what I mean to say, keeping the different types of loads, because you people have studied axial loads, torsional loads, and the bending loads. For each of the loads, you know how to calculate the stresses, and you can convert those stresses into either sigma x, sigma y, or tau xy or tau xy. Like this, every point in the material, very, very important, every point in the material is going to have whether any one of these three components or at least two of the components is going to have. Next comes the important question. Every point has these components, but at which point, every point has these three components, but at which point crack may initiate, or at which point yielding may start. It's a very, very big challenge for a design engineer. So in that aspect, people have come up with a new strategy. What they have come to know is fracture. That means breaking a component into two pieces can be done only by the either by the maximum normal stress or the maximum shear stress. Please keep it in mind. Fracture, I told you, I have shown you enough samples to understand fracture. So this fracture can take place either because of the maximum normal stress or the maximum shear stress. ఒక పాయింట్ దగ్గర ఫ్రాక్చర్ అవ్వాలి అని అంటే ఇట్ కుడ్ బి బికాస్ ఆఫ్ maximum normal stress or maximum shear stress. Then we are left with the two important questions. What do I mean by maximum normal stress? What do I mean by maximum shear stress? Having known these three components of stress for a two-dimensional problem. See, there are very complex theories are there to work in 3D, and n number of theories are there. And when you people want to really pursue design engineering and take up PhD, there you will come to know enough theories and lot of headache will come into picture. But this theory, what I am presenting, is the much simpler, and so that you all can understand very coolly. So now, having known the sigma x, sigma y, tau xy, next job is I want to find out at a given point in a material, what is the maximum normal stress and maximum shear stress. Very well said. Now, this maximum normal stress and maximum shear stress at a point in a material are what people started calling them as the principal stresses. I hope with this much of explanation, you people have become very, very comfortable with the principal stresses. So principal stresses at a point are nothing but the maximum of the normal as well as the shear stresses. Okay, yeah, next comes the very important question. Now let us focus, how do I calculate these principal stresses at a point in a material, because I know they have to be maximum. Please keep it in mind, they have to be maximum. So simply I adopt some maximization technique and try to come up with the principal stresses. So I skip this problem because this you can easily understand. And yeah, now I come back here. Now I come back here, dear friends. I have taken a stress element, and this is in 2D. I have only three components, sigma x, sigma y, and the third component is tau yx or tau xy. Because these two are same, I cannot treat them as independent. So one of them only I take it as independent. So I have only these three stress components. So all these directions, to begin the show, we treat them as positive, and we will move ahead having attached a coordinate system x, y, and z. And in this one, z is coming out of the presentation. It's coming out of the laptop screen. That is the direction of z, because we need to follow right-handed coordinate system. Right. So now I have chosen how many planes, and yeah, I have chosen this as a one plane and this as one plane. So only 4 planes I have chosen, and on these 4 planes I know what are the stresses acting on this plane, dear friends. One is sigma x and tau xy. On this plane, sigma y and tau xy. On this plane, sigma x and tau xy. So like this, I know what are the stress components acting only on the 4 planes. Now comes, because for the failure to occur, I need to really focus on maximum normal and maximum shear. But I really do not know upon which planes this maximum normal is going to act and the maximum shear is going to act. Please understand the crux here. These are the four planes and these are the stress components. And this may not be the maximum normal, this may not be a maximum normal stress, and this may not be the maximum shear stress. Then what I need to do at this particular point, I need to keep drawing infinite number of planes. I need to keep drawing infinite number of planes, and I need to go to a plane upon which I think there is a maximum normal stress, and I need to choose another plane upon which I think there is a maximum shear stress. So finding the planes of maximum normal and maximum shear is nothing but what we call it as a principal stresses and the corresponding principal planes. Principal plane is a plane upon which either the normal stress is maximum or minimum or the shear stress is maximum. Okay, so to do that, what we do in this stress element, I take a wedge shape, I cut it here, dear friends. I cut it here, and this plane, this new plane I have generated. Earlier I know I have this plane for me and I have this plane. So now I have created a new plane here at an angle of theta to the vertical, and I know what are the stress components acting on these faces. You know, upon this face there is a sigma y, and upon this face there is tau xy. Upon this face I know there is sigma x, and upon this I know tau xy. Only stresses I am talking. Next, what I do upon this inclined plane, that is inclined theta to the vertical, this is the plane I am focusing. Upon this plane, dear friends, I want to know what is the maximum normal stress. I want to know what is the maximum normal stress on this one. And upon this plane, I want to know what is maximum shear stress. That is our objective in principal stresses. Having known sigma x, sigma y, and tau xy. So for that one, what we do, I draw a normal to this wedge shape. That is definitely going to be at theta to this horizontal x-axis, and let me assume sigma n is the normal stress acting on this plane which is inclined at theta to the vertical, and let me assume tau subscript nt as the shear stress acting on this plane which is inclined at theta to the vertical. I'm assuming, we have to assume. So these two new stresses I have assumed at an angle of theta. Then what I do, because it's a wedge shape, I go on writing the equilibrium equations. Sum of the forces in the normal direction should be 0. Sum of all the forces in the transverse direction. This is shear direction. We do also call it a transverse direction. So because I know these components, and I assume the area of the hypotenuse as delta A. Baga chudma, area of the hypotenuse, let me take delta A. So if I take this one delta A, I can find what could be the area of this opposite side. So it will become dA sine theta, and I can find out what is the area of this adjacent face, that is dA times cos theta. So having known the areas, having known the stresses, you know very well, stress multiplied with the area is going to give us the forces. So tau yx dA sine theta is the force acting here in the negative x-axis, and sigma y dA sine theta is the force, normal force acting in the negative y-axis. And like this, totally I have 6 force components, 1, 2, 3, 4, 5, 6. All shown in the blue color are normal. All shown in the brown color are the shear forces. Now very simple, you all know very well. I want to balance all the forces in the normal direction. In this direction I want to balance the forces. Perpendicular to this I want to balance the forces. You know how to resolve the forces along x and y axis. So if we resolve all the forces in this normal direction, dear students, sum of all the forces in the normal direction, sigma Fn, is equal to first this force acting on this plane, that is sigma n into area is delta A, dA. And if you see this component tau xy dA sine theta and cos theta, dA sine theta, Okay, this is the sine theta. And if you split it into two components like this, dear friends, so it is opposite to this normal direction. So this will become a negative term for us. And similarly, if you take this tau xy, it is acting like this. And if you split it parallel and perpendicular to this, like this, dear friends, okay, it is also going to be a negative component. So one more minus component. And sigma x, if you take, it is like this. So you also split this into two components, like this and like this. So it is also opposite to my normal direction. So it is also becoming minus. And even sigma y, you break it here, see, it's going to be negative. So you balance all the forces in the normal direction. This is a simple equation we all can get, and today you can go and you can write with the pen all these equations very comfortably. And we know that tau xy is equal to tau yx because of the complementary nature, and simply you solve it. I got very important equation. This is the normal stress on a plane which is inclined at theta degrees to the original x. If I take this one as original x-axis, this is the normal stress I got on a plane which is inclined at theta to the original x. Very good. Now next, what is my objective? My objective is to go to a plane upon which this normal stress is maximum. And if you look into the equation, because sigma x, sigma y, 2xy and 2 are constants, only theta is the variable here, that is the parameter. So I want to maximize this sigma n. You know, from mathematics, to maximize a function, we take the first derivative and equate it to equal to 0. And to check whether it is really maxima or the minima, then we take the second derivative, and based upon the sign, we decide it. Okay, so now we try to take the derivative of this d sigma n by d theta, equate it to 0. We are going to get a relationship for theta corresponding to a plane upon which this normal stress is going to be maximum. Yeah, so that is what precisely we have done. Next, similarly, if I balance all the forces in this direction, if I balance all the forces in this direction, because earlier we balanced in this direction, now I balance in this direction, same 6 components you are going to have, but the other part of the force vector you are going to get. So accordingly, if you balance all the forces in this one, we are going to get the second expression. From this one, if I write the expression for shear stress that is tangential to the normal, shear stress tangential to the normal, we are going to get this expression for the shear stress on a plane whose inclination is theta with the original x. So I got expression for normal stress, I got expression for shear stress. Now objective, according to the failure, we want to maximize them. So to maximize them, the very next question is we are going to work with the differentiation. So to make the differentiation pretty simple, people have introduced a few trigonometric identities so that the problem can easily be manipulated mathematics wise. So we know that cos square theta is equal to half of 1 plus cos 2 theta, and sin square theta is half 1 minus cos 2 theta, and sin 2 theta is 2 sin theta cos theta. Just plug in these identities into these two expressions and simplifying, we are going to get this as the normal stress expression, and this is for the shear stress expression. Having got them, dear friends, now we are going to what you can say, take the derivatives, that is to find the maximum normal and maximum shear. Okay, right. So having said, this is what we are going to do. If I want to find the plane upon which the normal stress is maximum, I need to differentiate the sigma and what I got with respect to theta and equate it to 0. So this is what is the differentiation we are going to get, and simplify it, because here I have sine and cos. So from this I can write tan 2 theta to be equal to tau xy by sigma x minus sigma y by 2. I think this you might have by hearted. Tan 2 theta p is equal to 2 tau xy by sigma x minus sigma y. And this corresponds to the maximum normal stress. So therefore, this theta, we do attach a subscript p to say that it is a principal plane. tan 2 theta p is equal to this. So this expression tomorrow, having known sigma x, sigma y, and tau xy, dear students, if you substitute, you are going to get the value of theta p. And this theta p, if you take with respective to the original x, and if you draw the plane, upon this plane, normal stress is going to be maximum. That is what is the final underlying fact. And this is a tan 2 theta p, so that it is going to have two values which are at a gap of 180 degrees from each other. So this expression gives two values for 2 theta p, and which are at 180 degrees apart. And when I convert it into theta p, these two are at 90 degrees to each other. Right. So let us not waste much time, because the fundamentals I have told you, and all these remaining expressions anybody can work out. But coming here and the strategy, how did we come here, is more important. Then if I look back for the in-plane shear stress, but let me not even go more here, because a lot more I need to explain here if to make you people understand this. But let us call for timing in-plane shear stress. So I take the shear stress that is on the normal plane in the tangential direction and differentiate it with respective to theta equated to 0. I got an expression for theta s, which corresponds to the angle a plane makes with respective to x, upon which shear stress is maximum. So tan 2 theta s is equal to minus sigma x minus sigma y by 2 by tau xy. But if you observe this tan 2 theta p and tan 2 theta s, they are one and the same, but one is reciprocal to the other. Okay, this is reciprocal, not inverse. So tan 2 theta p is reciprocal to the tan 2 theta s. So if you work out mathematics and try to say this tan 2 theta s into 1 by tan 2 theta p reciprocal, and the product should go to 1, very easily we all can prove that algebraic sum of theta s plus theta p will turn out to be equal to plus or minus 45 degrees. So this is a very strong outcome we can derive based upon the reciprocal nature of two functions in this trigonometric approach. Okay, so that means a plane of maximum shear and the plane of maximum normal, they are at a gap of plus or minus 45 degrees. So plus 45 means it is counterclockwise, minus 45 means it is clockwise direction. So this is how we are going to find theta s and theta p. Once you get theta s and theta p, dear friends, back substitute this theta p and theta s into this sigma n expression, you are going to get what you can call it as two normal stresses for two thetas. One of them is going to be the maximum and one of them is going to be the minimum. So these two are what we call them as the principal normal stresses. And the theta s you have found out, bring it here and substitute that theta s into this. Okay, bring that theta s into that. You will find that upon this see, this is what is I'm talking, theta p, you know it. Bring this theta p, substitute here, we got sigma max and sigma minimum. Bring this theta p and substitute into this shear stress expression. You all will find today, please try, go home. You will find this one to be turning out to be equal to 0. So the fundamentally what I can say, the planes upon which a maximum or minimum normal stress acts, there is no shear stress. It's a very good question. Competitive exams, you may face it. Okay, right. So having said that, then you can substitute this theta s into the shear stress expression and you can come up with the maximum shear stress. So now, having said that, two normal stresses we are going to get. One is principal stress 1, one is principal stress 2. This is maximum and minimum. This is a simple expression everybody will by heart, including myself way back. So in the problem you will be given sigma x, sigma y and tau xy. You can quickly calculate what is sigma p1 and sigma p2. Okay, right. And then now, and this is the expression we do evolve for the maximum shear stress. Maximum shear stress. So finding the sigma 1, sigma 2 and tau maximum are nothing but what we call it as the stress transformation or the principal stresses. ఎందుకు దీన్ని స్ట్రెస్ ట్రాన్స్ఫర్మేషన్ అంటున్నారు అని అంటే బై రొటేటింగ్ ద ప్లేన్ అట్ ఏ పాయింట్ వీఆర్ రొటేటింగ్ ద కోఆర్డినేట్ సిస్టమ్. Our original xy is getting shifted to a new position, so there is a transformation. So in this transformation, even the stress components are getting transformed, therefore it is called as a stress transformation. And the beauty, finally I want to tell you, into this shear stress expression, dear friends, if you come here, this is the shear stress expression, and into this shear stress expression, if you try to substitute, okay, this normal, this theta s, if there no theta s, you plug in this theta s into this sigma n, plug in theta s into sigma n, you don't find sigma n to be equal to 0, but there is some amount of normal stress. So that indicates final conclusive takeaway. Planes upon which maximum normal or minimum normal stress acts, shear stress is 0. But the planes upon which maximum shear stress acts, there is some amount of normal stress, which we can get by substituting into this expression. Okay, yeah. So having said, dear gentlemen, and this is the average shear stress, that average normal stress that is going to act on the principal planes. And to find these principal planes, there is even a Morse circle approach is there. Let me not get into its construction part. So this is the original stress element with which I began the life, and this is the normal stress or the principal stress element, and this is the shear stress element. So you all should be in a position, if this is given to you, you all should be able to draw this stress element and this element. Then this will give a passage for us to enter into the original design, wherein I can design the components to avoid the failure from fracture, yielding, and stability. So right, so with this because this is a sample problem, you all can solve, because there are enough problems in enough books, but try to always read some very good foreign author books where very good number of problems are solved. You can develop a very good concept. And so now I want to, is Raghu sir here? Raghu sir, are you there?
Sir, చెప్పండి సార్.
Sir, do we have how much time we are left with?
Still we have, you can carry on, sir. Still we have 10 to 20 minutes, sir.
Okay, in 10 to 20 minutes I will try to close. I will take people to the quickly theories of failure. Just చెప్పి వదిలేద్దాం. Okay na?
Okay, sir. Okay, sir.
All right, thank you. So dear students, and so dear students, if you have before I move forward to theories of failure, till now if you have got anything to ask me, you are more welcome. Okay, so now having said, now we will go to I'll try to share something new, and now let me present what you can call it as this. Raghu sir, is my PPT visible to you now? Design against static load.
Yes, sir. Visible, sir.
Okay, thank you so much.
Okay,
so now so dear students, having said that, till now what we have done is a very important calculations we have made with regard to the stresses, and we calculated sigma 1, we calculated sigma 2, and we calculated tau max. Okay, now how do we use these three to predict the failure of a material is what all about the theories of failure. So theories of failure we have with regard to the static load, we have with regard to the fluctuating loads, and we have with regard to the buckling loads also. So every load has got its own theories of failure. So in theories of failure, basically what we do, these maximum normal or maximum shear stresses what we have got, as I told you, any component, we will go to one point, there is a stress acting, and every point has inherent strengths. So the strengths of the component, especially with regard to isotropic materials, you know, we all have done a stress strain curve. Isotropic materials are characterized by ultimate tensile strength and yield strength in tension, ultimate compression strength, and ultimate tension. So these are all the strengths. So you need to understand the difference between the strength and the stress. Stress ante it is the state, This can be zero, this can be maximum. What is strength? Strength is nothing but the capacity of the material to bear the load. సో అంతకంటే ఎక్కువ కనుక లోడ్ వేసేస్తే ద కాంపోనెంట్ ఈస్ గోయింగ్ టు ఫెయిల్. సో దీస్ two strengths we need to have in order to go with the theories of failure. So theories of failure are the hypotheses predicted by so many people to predict the failure of a mechanical component. And this I want to skip because these are very small things for you people. If there is an axial load, this is how we do calculate the normal stress. And if it is a shear, this is how we calculate the shear stress. And with regard to the bending of problems, we use a sigma is equal to my by I. And lastly, with regards to torsion, I can calculate what is the tau x y. So having known them, then coming back to the plane stress, we have enough discussed. So then came the theories of failure. So theories of failure provide a relationship between the strength of the machine component subjected to a complex state of stress with the mechanical properties. So finally, there is a component. Let us say its carrying capacity is only 100 and I am loading it to 120. Common sense tells this component is going to fail. And there is a material whose capacity is 100, and if I load it 80, 90, 95, at least to a great extent, I am very sure this component is not going to fail. So this is a simple philosophy we adopt in the theories of failure. So many people have made great efforts in proposing them. And we have generally used 5 theories of failure: maximum principal stress, maximum shear stress, and distortion energy, and maximum strain and total strain energy theory. So what is maximum principal stress theory says? Maximum principal stress theory states that the failure of a mechanical component takes place. Failure of a mechanical component takes place when the maximum principal stress reaches the ultimate strength of the material. Very, very important point. According to this theory of failure, who proposed by the Rankine in 1850, failure will initiate when the maximum principal stress becomes equal to ultimate strength. So according to this theory of failure, we will finally write, because lot much is there for me to explain, but let me brush up so that you might have got some idea. So finally, according to this theory of failure, if you want to decide the failure, we need to calculate the normal stresses. So at any point in a material, we have 3 normal stresses: sigma 1, sigma 2, and sigma 3, and we want them to be maxima or minima. So therefore they are the principal stresses. And if sigma 1 is equal to SYT by factor of safety, or if it is equal to SUT by factor of safety, this is a limiting value. This is the maximum limit to which this sigma 1 can reach. Anything over and above this will contribute to failure. So this is a simple expression, and it's a straight line equation, and it is a constant. So therefore, if you draw it in a 2-dimensional space, taking sigma 1 along x-axis and sigma 2 along y-axis, you are going to get a failure envelope, which basically more or less looks like a square if yield strength in tension and compression or ultimate strength in tension and compression are equal. So with this also, we can predict the failure of the component. And this sigma 1, how do I calculate? Already we have shown expression. The sigma 1 is nothing but sigma p1. That is sigma x plus sigma y by 2 plus or minus, and that value. Secondly, we have the most widely, to a large extent, second theory of failure, that is a shear stress theory of failure, which is due to Coulomb, Tresca, and Guess. These 3 people have combinedly proposed it, and it is most widely used theory of failure. And here I want to just quote one example. And you all have done a universal tension test on a UTM, and if you observe the specimen, you all have studied this, and there is a question also in the lab exam. You are going to get the cup and the cone structure for typical ductile material. Please, material is very important. If you conduct UTM test on a typical ductile material, dear friends, and if you observe the failed surfaces, one of the component is going to have a cup, and the other is going to generate the cone sort of structure. And most probably, if you draw the line along these failed surfaces, you find it to be inclined at 45 degrees to the loading axis. Why this 45 degrees? Because if you go to the stress transformation and try to submit that theta is equal to 45 degrees, you will find shear stress to be maximum on a plane which is inclined at 45 degrees. So this has given so many engineers a conclusion that ductile materials always mostly fail in shear. It is very important point. Ductile materials always fail in shear, whereas brittle materials always fail in normal mode. So this theory has got a lot of prominence. And according to this theory of failure, if the maximum shear stress, what I have calculated according to the principal stresses explanation, if it is equal to SYT by 2, the component is going to fail. And accordingly, we have another theory of failure, distortion energy theory of failure, the most widely used. It is above the shear stress theory of failure, and the most widely used, and it is always there in all packages, and we do call it as a von Mises, who contributed a lot. And with regard to this, there is so much I have got to discuss, and anyway, we literally ran out of time. Let me not get into that. But the important aspect of this theory of failure is this theory focuses on distortion energy. So what is distortion and what is non-distortion? Two things we need to understand. If you take a ball and try to compress it from all the sides equally, the ball shape remains the same, but the size will reduce. That means ball did not get distorted. So the energy corresponding to that is what people call in mechanics of materials as a dilatation. Dilatation. But some block you take and try to apply load, if the shape is changed, okay, then we can call that the component has been distorted. So these three people combinedly, they have proposed and said that the failure of the component mostly takes place only because of distortion energy, that is change in shape. And accordingly, we need to calculate these two energies, and we have to come up with only distortion energy, and we need to link it to the material properties. So according to this theory of failure, in 2D, the governing equation for the failure is yield strength by factor of safety is equal to root of sigma 1 square minus sigma 1 sigma 2 plus sigma 2 square under root. So if this is violated, then the component is going to fail. So like this, dear friends, we have another theory of failure which is not so important, like a maximum strain and Huber total strain energy theory of failure. And with these things, I sincerely feel that I have given some insight into the mechanics of materials with regard to principal stresses and with regard to the theories of failure, which is the most important part of all mechanics of materials and the design engineering. So with these few words, thank you so much, dear friends, for having listened to me and for having me here. And it is goodbye from my side. So now it is over to Raghu sir.
Thank you, sir. Thank you for your valuable information, sir. And thank you all the students. And special thanks to the management Guru Nanak institutions and principal sir for providing the opportunity. And thank you HOD sir for supporting us. Thank you, sir.
So thank you, Vijay Kumar sir and Shilari sir and Raghu sir. And it's very nice joining you. And
Yes, sir.
it's bye from my side and good day.